And that's tissue injury or cell injury as a result of exposure to free radicals or reactive oxygen species. Okay. A free radical, raise your hand, what's a free radical? Everybody know the definition of a free radical? Let's see a brave hand. Yes, ma'am. Exactly. A free radical, exactly. A free radical is an element that has a single unpaired electron in its outermost shell. Okay. So a free radical is some sort of species, some element that has a single unpaired electron in its outermost shell. Okay. Electrons are very lonely structures. They do not like to exist alone. Okay. And in fact, they won't exist alone for very long, because they will very rapidly, a free radical will very rapidly find an electron and steal it from another structure. Okay. It will steal it from some sort of any kind of substance, whatever compound it comes in contact with. It will steal it from bonds that are between compounds. Okay. And in that process, it will create damage. So free radicals are incredibly reactive compounds, or incredibly reactive elements, because they have this unpaired electron in their outermost shell. So free radicals in our body are often in the form of what are called reactive oxygen species, meaning they are free radicals that contain oxygen in their structure. And there are many sources of reactive oxygen species, including, very importantly, they are a product of normal metabolism. Okay. In the course of normal metabolism, a certain amount of reactive oxygen species are produced. Okay. Now, this is not usually a problem because we have endogenous antioxidants. We have endogenous substances that are designed to neutralize these reactive oxygen species. Okay. But that doesn't mean that we can't have an accumulation of reactive oxygen species that does damage. Okay. It's actually thought to be a normal process of aging, the damage that reactive oxygen species do. Okay. In fact, for the culture of the anti-aging process, the anti-aging movement, which is a very powerful movement in the United States, there's a lot of people that don't want to age, and there are some people that take it very, very, very seriously. And there's a lot of research into reducing the aging process, reversing the aging process. And one of the only things that's actually been well established to dramatically slow the aging process is consuming a drastically reduced caloric diet. Okay. And these are these dramatic caloric restriction people where they consume, I'm not talking about people who have an eating disorder, that they're anorexic or something like that. They may also be that. But we're talking about people who intentionally consume maybe 500 calories a day or something, and they don't look great, and they don't look like they don't look like Atlas, Shrugged or something like that. But they do tend to extend their lives significantly. Okay? And the idea is by reducing the metabolic load that their body has, they produce fewer of these reactive oxygen species, and that is what slows down the aging process. And it's really the only thing that's been shown to actually slow down aging. So you have a very long, unhappy life, but a long, hungry, unhappy life, but a long life. So these reactive oxygen species can do damage in a multitude of ways, but the three basic ways that they tend to cause cell injury is through a process called lipid peroxidation, and that's where these free radicals interact with lipids, especially in the membrane. Okay? Intracellular lipids, but also lipids of the membrane, and can cause membrane damage. Okay? They can interact and disrupt polypeptide chains. Okay? And obviously, all of the proteins in our body are polypeptide chains. So they can disrupt the function of a wide variety of proteins, including enzymes, including structural proteins, and they can do DNA damage. Okay? They can break and interrupt bonds between nucleic acids in the DNA structure, and they can cause damage that way. Okay? So to go back to this idea of reperfusion injury, when we have reperfusion injury, but what we're really doing is we're layering injury on top of injury. Okay? So when someone has reperfusion injury, the first injury that's happened is a hypoxic injury as a result of ischemia or cessation of blood flow. Okay? That's injury number one. They've sustained hypoxic injury. Now, the way the body responds to tissue injury is by initiating an inflammatory response. Okay? And we talk a lot about inflammation in the immune system, but one of the steps in the inflammatory response is the delivery of neutrophils to the area. Okay? So neutrophils arrive at the site of inflammation, and part of what they do is to sort of debride a wound, right, where they're trying to actually cause damage in order to clear dead or tissue that is either dead or injured. Okay? And part of how they do that is they actually release reactive oxygen species. The neutrophils do. Okay? So the first layer of injury was this hypoxic injury. The second layer is inflammatory injury. And then the third layer comes with the reintroduction of blood flow, because any amount of blood delivered anywhere that contains oxygen is also going to contain a certain amount of reactive oxygen species. Okay? So the first layer of injury was the hypoxic injury. The second layer was the inflammatory injury, right, and the neutrophil release of reactive oxygen species. And the third layer of injury is the return of blood flow and the introduction of even more reactive oxygen species. Okay. And so usually reintroducing blood flow to an area is done using drugs that are designed to scavenge some of these reactive oxygen species in order to prevent the reperfusion injury. Okay. Okay. So what happens to a cell with hypoxic injury? So a little bit more detail about the mechanisms, some of these mechanisms of cell injury. And we, like I said, we know quite a lot about hypoxic injury. It's a really common form of cell injury, and a lot of what we know about it comes from studying heart disease and myocardial ischemia, myocardial infarction. And so some of the details of this has been worked out. Okay? And so first off, we get, at the top here, obstruction or cessation of blood flow. Okay? So blood flow is limited, okay? Which creates ischemia. It is ischemia. Okay? Now, immediately, the first result is we have less oxygen going to that tissue. There's less oxygen being delivered to the mitochondria, the site where oxygen is actually needed, where it's consumed. Okay? So the reduction in mitochondrial oxygenation reduces ATP production. Right? That's that crisis of energy. Our ability to produce ATP goes down dramatically. And part of the compensation for this is that we actually start increasing our rate of glycolysis, trying to produce any amount of ATP that we can. Okay? If we can't move forward with oxidative phosphorylation, we're increasing the rate of glycolysis. Now, glycolysis produces lactate or lactic acid. Okay? As the rate of glycolysis goes up, the rate of lactic acid production also goes up, and the inside of the cell becomes more acidic. Okay? And this can become a very dangerous situation, because as the cell becomes more acidic, you get changes in protein structure, including you get nuclear chromatin changes in the structure of the of chromatin within the nucleus. You can get very dangerous situation. You can get damage to the membrane of the lysosome, okay, including swelling of the lysosome. I can't read this because I can't see. And then the absolute worst case scenario is that this lysosome breaks down. Okay? And all the digestive enzymes within it spill into the inside of the cell. Okay? And when that happens, you really start to see autolysis of the cell. Okay? When the lysosomes explode, that cell is going to die. Okay? You can't survive being consumed internally. So the cell is going to start to die if those lysosomes break. Okay? In addition to this, decreasing the production of ATP, okay, something like 70–75% of the energy of the cell, the ATP production of the cell, is actually dedicated to operating our good old friends, the sodium-potassium ATPase pumps. Okay? The cells invest a significant amount of ATP into operating those pumps. And when ATP production goes down, those pumps start to go down. Okay? The function of those pumps start to go down. Okay? The result of that is you get this accumulation of intracellular sodium, this accumulation of extracellular potassium, and an accumulation of intracellular calcium. Okay? Because the sodium-potassium pumps use ATP. We also have calcium ATPase pumps. We have these calcium pumps that are constantly pumping calcium out of the cell. Okay. Now, when we have an accumulation of intracellular sodium, water follows that sodium. Okay. So as the sodium inside the cell accumulates, so does water within the cell. So the cell starts to swell. Okay. When we have an increase in intracellular sodium and calcium, we also have an increase in the excitability of the cell. Okay. So the cell starts to become unstable in terms of its excitability. Intracellular calcium starts to increase. You get all of these inappropriate reactions getting started, okay, that can be quite toxic to the cell. And this accumulating water within the cell and this acute cellular swelling, the point of no return for this swelling within the cell is when you start to get the bloating of the mitochondria, when you start to get the bloating of the endoplasmic reticuli, and then if you remember, the rough endoplasmic reticuli had all these ribosomes attached to them. And so when the ER starts to get bloated, those ribosomes actually start to detach. And so now you start to get the breakdown of structure that is essential for the cell's function. Okay? So a certain amount of cell swelling, the cell can rebound from that. But once you start to really get the breakdown of organelles, the cell is on its way to necrosis. And then off to the side here, this ischemia, this hypoxic injury, is going to be responded to by the body through what? that I just mentioned? How does the body respond to injury, tissue injury that I just said? Inflammation, okay? So you're going to get these white blood cells that come to the area, including neutrophils, and they are going to release a cocktail of nasty stuff, including the reactive oxygen species, and they're going to do, among other things, cause membrane damage. Okay? And the membrane damage is going to change the structure of the lipids and the lipids within the membrane. You're going to get the movement of inappropriate substances in inappropriate directions, including changes in calcium influx, which is going to compound the problem. Okay. So hypoxic injury is really about an energy crisis for the cell, predominantly about an energy crisis for the cell, and an inability to maintain normal function because it doesn't have enough energy to do the normal work of maintaining energy, maintaining function. Okay. And the very immediate result are these swollen cells that are well on their way to dying. Now, injury through exposure to free radicals or reactive oxygen species, I mentioned this before, that reactive oxygen species, here are some examples. These are compounds or elements that have one unpaired, or two, in some cases, unpaired electrons in their outermost shell. Okay? Now, an unpaired electron in its outermost shell is an incredibly reactive species. Okay? It's going to interact and react with anything it comes in contact with. Okay? And so one of the mechanisms of injury is this lipid peroxidation. And the lipids that often are a target of peroxidation are membrane lipids. Okay? And so peroxidation of membrane lipids, it can increase the membrane rigidity. Okay? It can make that membrane less fluid. It can decrease the activity of membrane-bound enzymes, okay, including damaging the sodium pumps. It can alter the activity of membrane receptors, okay? And it can alter permeability. Okay? It can actually create losses of integrity to the plasma membrane, which end up causing influxes of water or calcium or anything else that's inappropriate. Now, there's a lot of sources for the production of reactive oxygen species. Okay? There's a lot of sources for the formation of these reactive oxygen species. As I mentioned, metabolism. So these reactive oxygen species are a normal product of aerobic metabolism. Okay? Any organism that can carry out aerobic metabolism produces these reactive oxygen species. Okay? But they also produce these endogenous antioxidants that can neutralize most of it. Okay? So normal metabolism, that oxidative metabolism that occurs at the mitochondria, produces these reactive oxygen species. Inflammation is a source of these reactive oxygen species. They are released by some of the white blood cells, especially the neutrophils. Okay, and whenever we have inflammation, neutrophils are recruited to the site of inflammation. Okay, and one of the things they do is dump out a bunch of reactive oxygen species. Okay. Exposure to UV light can produce reactive oxygen species. Exposure to environmental pollutants in the form of air pollution, the normal sort of industrial air pollutants that interact with UV light in the environment can produce reactive oxygen species. Combustion and exposure to elements within cigarette smoke can produce reactive oxygen species. Ionizing radiation is a source. So these reactive oxygen species, the generation of these species can be increased through the exposure of multiple sources. Okay? And they once generated, they can all cause damage in these various ways. Okay? So those are two really important mechanisms of cell injury. A lot of the drugs that are cytotoxic that we consume, so a lot of drugs that are thought to be sort of poisonous drugs, they are often cytotoxic because they increase the production of reactive oxygen species. Okay? So a lot of these various individual examples of how you can have cell injury or what can produce cell injury, they sort of converge often on deprivation of oxygen, hypoxic injury, and injury through exposure to free radicals or reactive oxygen species. Okay? So those are some sources of cell injury. What are some manifestations of cell injury? So these manifestations of cell injury are often adaptations to persistent injury. Okay, they're usually adaptations to persistent injury. And the one important exception to that is dysplasia, because dysplasia, although it is a result of cell injury, it's not adaptive. Okay? It doesn't benefit the cell. Okay? But these other adaptations are a strategy for the cell to maintain stability in the face of this persistent injury. And it includes things like atrophy. So atrophy is where the number and size of cells are reduced. Okay? Atrophy is where the number and size of cells are often reduced. Okay? Sometimes the number stays the same, but with atrophy, the overall size of cells are reduced. Okay? And we're not talking about cell shrinkage. We're talking about a complete and proportional scale down of cell mass. Okay? That's atrophy. Hypertrophy is where the number of cells stay the same, right? Cellularity stays the same, but cell size is increased. Okay? And again, it's not cell swelling. We're talking about a proportional scaling up of cell size and cell mass. Hyperplasia is where the size of cells is constant, but the number of cells has increased. Okay? The number of cells has increased. And metaplasia and dysplasia are alterations of cell differentiation. Okay? And I'll talk about that more in a second. I'll wait to define metaplasia and dysplasia until I have a chance to talk about cell differentiation. So, first of all, let's talk a little bit about cell atrophy. So, when we talk about any of these adaptations, what you'll find is that many of them have what's called a physiological form and a pathological form. And that means that when something is physiological, when you're talking about physiological atrophy, you're talking about something that happens as a result of normal physiological function. Okay? So there are certain times where atrophy is physiological, it's normal. And that usually occurs during development. Okay? So there are certain structures in our body, especially development of the central nervous system, where structure develops and then gets sort of pruned back. Okay? Where structure develops in sort of an unregulated way, and then for example, when it comes to the central nervous system, certain cells and synaptic connections are reinforced and elaborate, and certain cells and synaptic connections are not used and therefore sort of atrophy, and the overall structure is pruned, okay? So that all the energy goes to only the most important structure. Okay? So that's physiological atrophy. That's part of normal embryonic and fetal development. Pathological atrophy occurs because of a couple of different possibilities. Physiological atrophy can happen because, number one, and the most common cause of pathological atrophy, most common cause is a decrease in functional demand. Okay. Another way to describe this is disuse atrophy. Okay. And this is really clear when you have someone who maybe breaks a bone, the limb gets casted, and then 2 months later or something, when the cast comes off, the limb, let's say it's an arm, looks really thin compared to the unaffected limb. Okay? And that's because a lot of that muscle tissue has atrophied, has gotten smaller because of disuse. This is a very, very, very common, very common form of atrophy. Other forms of atrophy, pathological atrophy, are a result of, for example, decreased oxygen delivery chronically. Okay. So we're talking about, let's say, very, very mild hypoxia, that the kind that's tolerated over time, but it requires tissues to scale down metabolic need, and so the tissue gets smaller. Okay. Or prolonged deprivation, nutritional deprivation can cause atrophy of tissue. Okay. Again, it's tolerated, but it requires tissue to react by scaling down metabolic need. And then another example of pathological atrophy is atrophy that results as a result of decreased trophic signal. Okay. And a trophic signal is a signal that promotes growth. What body system are we used to hearing the word trophic? I heard somebody say the endocrine system. Okay? And so a lot of examples of atrophy as a result of reduced trophic signal can be drawn out of the endocrine system. So if you remember the relationship between thyroid stimulating hormone and thyroid tissue, right, the thyroid gland. Thyroid stimulating tissue increased the production of thyroid tissue. So if there were a situation where TSH levels were chronically low, the thyroid gland might actually atrophy, because there's a reduction in this chronic trophic signal that maintains the structure of the thyroid gland. Okay. And the example that the images that are on the slide here, this is actually a slide of liver tissue, both healthy liver tissue in the upper left here, and atrophied liver tissue as a result of essentially starvation. Okay. So prolonged protein or caloric deficiency causes the liver to scale down its structure and atrophy to a certain extent. And what's common among these examples of reversible cell injury is that they are reversible, okay? That they are not permanent changes. So hypertrophy is sort of the inverse of atrophy. Okay, hypertrophy is the inverse of atrophy, where you have cell size getting scaled up, increased. And you also have physiological hypertrophy and pathological hypertrophy. Physiological hypertrophy is the result of two possible things. Okay? Physiological hypertrophy can be a result of increased functional demand that is not pathological. Okay? So increased functional demand within the normal parameters of the function of that tissue. All right? And if you want to see examples of that, just go to the gym and hang out on the weightlifting floor, right? You may or may not see examples of that, but you will likely see at least a few, all right? So this is where you're increasing the demand on tissue, and the tissue is adapting by increasing in size. And that's it's physiological because the increase in size increases the functional capacity of the tissue, but still within its normal range of functional potential. Okay? Another place where you see hypertrophy is, again, at different developmental stages. And usually this developmentally regulated or developmentally connected hypertrophy is regulated by changes in hormone levels. Didn't come from me. I have no idea. They are related to changes in hormone levels. Okay? And so early on in development, when your body is instructed to develop as a female anatomically or male as anatomically, certain cells hypertrophy and elaborate in order to create the structure of a female or a male. And then at puberty, you get a lot more hypertrophy of particular structures as a result of an increase in hormones that direct that hypertrophy. Okay? That's physiological. Pathological hypertrophy is actually coming from the same sources of stimulation, but the stimulation is inappropriate. Okay? So number one, pathological hypertrophy is a pathological increase in functional demand. Okay? It's an increase in functional demand beyond what's normal for that tissue. And you're actually looking at, in this slide, an example of this. So what we're looking at here is actually the cross-section through cardiac tissue, cross-section through the heart. And we're looking at the two chambers, the two ventricular chambers. We're looking at the right ventricle here in the left, and then the left ventricle here. So if you notice, this left ventricle is very, very tiny, right? The space is really tiny because the left ventricular muscle is so thick. Okay? And so this is left ventricular hypertrophy. Okay, left ventricular hypertrophy. Does anybody happen to remember when the left ventricle contracts, where the blood goes next? What's that? The aorta, right? So one of the ways that left ventricular hypertrophy occurs is when potentially somebody's got a stenotic aortic valve. Okay? And the left ventricle's got to work harder in order to eject that blood. Or if someone has chronic hypertension, and the pressure within the aorta and the rest of the arterial system is elevated, and the left ventricle has to work harder in order to eject that blood. Okay? And so left ventricular hypertrophy, it is an adaptation to increased functional demand, but the increased demand is pathological. Okay? Because this thickening of the left ventricle, it reduces chamber size, it will reduce stroke volume and cardiac output. Okay? And so it creates pathological consequences. And it is reversible. Okay? If the source of the problem, the stenosis in the valve or the hypertension is relieved, this ventricle will go back to normal size. Another reason why pathological hypertrophy might occur is because of persistent tissue injury. Okay, persistent tissue injury. When tissue undergoes persistent injury, okay, let's say from chronic inflammation, right, chronic inflammatory injury, the cells are stimulated to increase their rate of turnover. The cells increase the rate of production because some of them are getting injured and die off. And sometimes that results in hypertrophy. Okay, so persistent tissue injury can cause hypertrophy. Also, a hyperstimulation by hormones. So oversecretion of hormone can increase the size of tissue inappropriately. Okay. And so we talked about TSH and the thyroid gland. Okay. When TSH levels rise, okay, the thyroid gland increases in size. And part of that increase in size is hypertrophy of thyroid cells. Okay. So often what goes hand in hand with hypertrophy, all the conditions that create hypertrophy, also can create what's called hyperplasia, okay, where you get an increase in cell number. Okay. So often hypertrophy and hyperplasia will occur together in a tissue. Some cells are non-dividing cells. They are cells that cannot increase in number. And so in those organs, in that tissue, you will only see hypertrophy. Okay? And that's why you never see left ventricular hyperplasia. Cardiac muscle cells can't divide. They can't make new cells. Okay? So you only see hypertrophy in cardiac muscle. Okay? But in other tissue beds, like the epidermal and dermal cells of your skin, you can see both hypertrophy and hyperplasia. Okay? And so the slide here we're looking at in A, the epidermal cells that are stained in this dark purple in a normal cell bed, in the normal skin bed, okay, in A, and then in someone who has a patch of psoriasis in B. Okay? And psoriasis is an autoimmune disorder of the skin where you have chronic injury through chronic inflammation, okay, to the skin. And the result is this increased cell turnover and a hyperplasia and hypertrophy of epidermal cells. Okay, and this thickening of the skin in certain regions. Okay. But so hyperplasia is very, very similar to hypertrophy in terms of where you have physiological hypertrophy and hyperplasia. Very, very similar. So developmentally, increased functional demand, that's physiological. Okay, you get hyperplasia as well. Okay. And pathological sources of hyperplasia is the same as hypertrophy. A pathological increase in functional demand, overstimulation by hormone, right, by hormone oversecretion, and persistent cell injury. Okay. Does that make sense? All right. So metaplasia and dysplasia. Metaplasia and dysplasia is a process that's connected to cell differentiation. Okay? And with cell differentiation, there are many tissue beds in our body where cells are constantly being replaced. Okay? where the cells in that tissue are constantly being replaced. And they're being replaced through this process of cell differentiation. Okay. And so with cell differentiation, you begin with some sort of adult stem cell line. Okay. You begin with this adult stem cell line that is tissue specific. Okay. And we've got lots of different adult stem cells that are tissue specific. One that we'll talk about a lot in the immune system is the hematopoietic stem cell in the bone marrow. Okay? So for these stem cells, they're not the kind of stem cells that are hotly debated or very controversial in the news, because they're not embryonic stem cells. Embryonic stem cells have a much wider possible fate. Okay? Tissue stem cells can only produce cells of that particular tissue. Okay? So hematopoietic stem cells of the bone marrow can only produce cells that are found in the bloodstream. Okay? And there's many cells that are found in the bloodstream. Okay? But they can only produce cells that are found in the bloodstream and white blood cells, okay, that are sometimes found in the bloodstream and sometimes found in tissue. Okay? So you start off with one stem cell that can become any of these bone marrow-derived cells. Okay? And then that one cell undergoes cell division and differentiation. Okay? And cell differentiation means that the fate of this stem cell gets narrowed. Okay? It becomes slightly more specialized. Okay? And so its fate has narrowed. And so these stem cells undergo multiple steps, multiple differentiation steps. Each of those steps narrows its fate. Okay? And then the final step, the final differentiation step, it produces what's called the terminally differentiated cell. The terminally differentiated cell. And there are two important properties to the terminally differentiated cell. The first property is that it's functionally mature. It's capable of carrying out the function of that tissue. Okay? So erythrocytes, red blood cells, are a terminally differentiated cell that's capable of carrying out the function of a red blood cell. Okay? The precursors before it were not functionally mature, couldn't really operate as functional red blood cells. Okay? The second important characteristic of the terminally differentiated cell is that it loses its ability to divide. It loses its ability to divide, which means that it has an expiration date. Okay? It's going to live out its life, it's going to contribute to the function of that tissue, and then it's going to die and be eliminated and be replaced by a newly terminally differentiated cell. Okay? And if you recall when we talked about, for example, the cells that make up the mucosal lining of the small intestine, right? They were these columnar epithelial cells, right? Where you constantly had a new crop of these cells migrating towards the tip of the villi of the small intestine, so that the small intestine was always populated with the healthiest, newest cells that are capable of absorbing nutrients and calories and everything else. Okay? And then the old cells just sort of died and got sloughed off and entered the GI tract and just sort of went through the digestive system. Okay? If you've ever taken care of a patient that was NPO for a prolonged period of time, right? Do they stop defecating? Do NPO patients that have been NPO for a really long time stop defecating? No. I mean, what they produce is pretty gross. But they don't stop defecating because all of the cells that are shed from your digestive tract, they've got to go through and get digested, and they make up what you're eliminating in the end. Okay? So this process of continuously producing a new crop of terminally differentiated cells is done through this process of cell differentiation. So when these cells that are terminally differentiated experience persistent injury, they often adapt or they change in either a way that allows them to maintain stability, or they change in a way that really deranges their function, okay, and compromises actually the health of the tissue. So the two alterations in cell differentiation that can occur is, number one, metaplasia. And this is where the terminally differentiated cell type in that tissue gets replaced by a less differentiated cell type. Okay? So in metaplasia, you have the terminally differentiated cell getting replaced by a less differentiated precursor cell. Okay? So, and we'll talk about that more in a second. And then with dysplasia, dysplasia is when you get complete derangement of that tissue bed. And you have complete derangement of that tissue bed. So the density of the cells, the size of the cells, the rate of cell division of those cells are completely abnormal for that tissue and not uniform. Okay. Dysplasia really describes tissue that has begun to completely ignore all controls over cell differentiation and division. What is that starting to sound like? Cancer. Okay? That's dysplasia is abnormal and it's precancerous. Okay? They are essentially cancerous cells that have yet to form a true tumor. Okay? So, talk about metaplasia. Okay? So metaplasia is adaptive. So a tissue bed that has replaced its terminally differentiated cell with a less differentiated immature cell, right? A precursor cell. Okay, and we've got a segment of cervical tissue here. The cervix is normally composed of ciliated columnar cells, which are found in a lot of different places. And over here we've got the replacement of these ciliated columnar cells with simple squamous epithelial cells. Okay? Also very, very common, in especially smokers, is the replacement of, in the airways, the replacement of airway, again, ciliated columnar epithelial cells with simple squamous epithelial cells. Now, this is an adaptation to persistent cell injury. Okay? Now, the adaptation is that these immature cells, these less differentiated cells, retain the ability to cell divide. Okay? They retain the ability to multiply and replenish themselves. So in the face of constant cell injury, they are better equipped to resist the constant cell injury. Okay? They can maintain the high cell turnover rate that's needed to maintain stability as a result of constant cell injury. So that's the adaptive part. The pathological part is that while they retain the ability to divide, they are not functionally mature. Okay? So for example, in the airway, simple squamous cells lack cilia. Okay? They lack cilia, which doesn't make them less silly. It makes them, I know, it's a stupid joke. It makes them less capable of clearing the airway as effectively as ciliated columnar cells. Okay? So the cilia on these columnar cells, normally in the airway, they're constantly beating their cilia, and that motion of the cilia creates this sort of constant motion, moving mucus and trapped dust and material, moving that material out of the airway. Okay? So when you've got, instead of those ciliated columnar cells, when you've got lots of simple squamous cells, you don't really have that natural motion to sweep mucus and other debris out of the airway. And so what you're left with is this need to mechanically move mucus out of the airway. And you get this very classic smoker's cough, which is especially bad when? In the morning, right? I heard the 5 smokers in the room, as they know. So it's especially bad in the morning because you've had you've had probably several hours of no sort of clearing your throat or coughing, right? And this accumulation of mucus. And I know, I used to be a smoker. I know what it's like. But luckily, my airway bounced back when I quit smoking because this is a temporary, reversible condition that can go back when the source of the chronic injury is removed. And of course, smoking is not the only source of chronic respiratory injury, but it's certainly a common cause of chronic respiratory injury. Now, one caveat to this, okay, so metaplasia is reversible and it is adaptive, but one caveat to this is if the source of the injury, right, the source of the persistent injury happens to also be a carcinogenic agent, okay? And a carcinogen is an agent that can cause mutations in cells that can create cancerous growth. Okay? So a carcinogen is a substance that can cause genetic mutations that promote cancerous growth. Okay? Which there are a laundry list of carcinogens found in cigarette smoke. Okay? So if the source of the chronic injury is a carcinogen, you have an increased likelihood or risk of the metaplasia becoming dysplasia and developing into cancer. Okay. So that's a caveat to the metaplasia discussion. Dysplasia occurs. Dysplasia, because it is really precancerous, it really is the development of cancerous cells that have yet to form a true tumor. Okay? And it doesn't mean that they will form a true tumor, but there are abnormal cells. Okay? Now, with dysplasia, just like with cancer, what's happened is you have genetic mutations in these cells. You now have a genetic mutation, and it's likely that you've got multiple mutations that's allowing these cells to ignore the normal controls over cell division and cell differentiation. Okay? And they resist differentiation, they maintain a high rate of cell division. Okay? and they ignore all cues to control those things. And that's dysplasia. Okay. And so what you find is, unlike non-cancerous tissue that's very uniform, okay, even the metaplasia, if we look back at that metaplasia, that simple squamous epithelial tissue looks like the simple squamous epithelial tissue that you'll find anywhere else in the body. It's very uniform. It follows sort of the same arrangement that you see simple squamous epithelial tissue. It's in an inappropriate place, but it is very uniform and stereotypical. But with dysplasia, there is a lack of uniformity. Cells can have different sizes and different appearances. And very importantly, the density of cells is usually much higher than the density of cells you find in healthy tissue. Okay. So cells, the number of cells are very high compared to what's normal for that portion of tissue. Okay? And they don't really care that they're dividing out of control and they're overpopulating the area. Okay? So, and this is some evidence of dysplasia within a section of cervical tissue. And the section of dysplasia is here on the right, and then the normal tissue, the healthy cells, the non-abnormal cells are on the left. And probably the thing that you can notice the most is the darkness and color on the right, okay, compared to the left side. And that's because the cellular density is so high and cells are packed in so tightly that you have more nuclear material, right? Less extracellular and intracellular cytosol occupying this space, and it's making it darker. Okay. Okay. So those are some of the major manifestations of cell injury. Another important manifestation of cell injury, or adaptation to cell injury, is altered intracellular storage. Okay. Altered intracellular storage is usually in the form of what are called cell accumulations or infiltrations. And this is where, in a cell, you see an accumulation, an abnormal accumulation of some substance. And usually that substance is, one of the more common accumulations is are lipid accumulations within the cell. Okay. But also what you can find are water accumulations, like vacuoles of water. What you can also sometimes see are inappropriate accumulations of glycogen. Okay. And sometimes what you'll see in cells are accumulations of material that is foreign. Okay. Material that's foreign. Okay. So someone who is chronically exposed to a lot of smoke might have accumulations of soot intracellularly in the cells of the respiratory tract. Okay. Cell accumulations are caused by two major things. It's an alteration in intracellular digestion. And either the intracellular digestive pathway is overwhelmed, or it's impaired, or it's a foreign substance and there's no natural intracellular pathway to digest it. Okay, so I lied, there's three. Okay, so these accumulations or infiltrations is really a problem with intracellular digestion. And so the digestive pathway could be overwhelmed, there's just too much substrate to digest, or it's impaired in some way. Maybe you have a deficiency of one of the enzymes that are necessary for the digestive pathway. Or the material being introduced is foreign and you don't have a digestive pathway for it. Okay. And so the strategy for adaptation in all of those cases, is to take that material and simply wall it off in a vesicle inside the cell so it can't interfere with other functions within the cell. Okay? But of course, as the infiltration gets larger and larger, eventually it is going to interfere with the cell function. So some examples of this altered intracellular storage, this infiltration or accumulation. Here we've got some lipid vacuoles, some vacuoles of fat within neuronal cells of brain tissue with someone who has a disorder called Tay-Sachs disease. And in Tay-Sachs disease, individuals have a deficiency in a very particular enzyme necessary for digesting a particular class of lipid. Okay? And so this is an example of altered intracellular digestion, okay? Where there's a deficiency in the enzyme necessary. Very, very common example of accumulation, infiltration, is fatty liver disease. Okay. So fatty liver disease is where you have hepatocytes in the liver with significant accumulations of fat. Okay. So normally hepatocytes have this sort of very nice, healthy rust color to them, and they don't have accumulations of fat in them. With fatty liver disease, you get enough of this accumulation, enough of this fat accumulation intracellularly, so that the gross structure of the liver looks different. The gross structure of the liver takes on this sort of paler appearance. It can actually have sort of a greasy appearance to it. Okay. So some of the ways that fatty liver disease occurs. Fatty liver disease is intentionally produced in a goose. Does anybody know what the foie gras, right? So so foie gras is this delicacy where a goose is force-fed a very fatty diet, literally force-fed, tube down the throat. And all of that fat, all of those high calories is sent to the liver, and the liver's ability to break down that fat is just overwhelmed. And as a result, you get this delicious fatty liver disease. I've never had it, but I hear it's delicious. That becomes a delicacy. Okay. Another example of sort of the same process, which was intentional but not in the same way, if you've ever seen that movie Super Size Me, right? That guy gave himself fatty liver disease after 30 days of eating nothing but McDonald's, right? So all of the metabolic panel, all of the indices of liver function looked like someone who was alcoholic, right? Because his liver had so much fat accumulation, it interfered with liver function, right? And so as soon as he went back to his normal diet, his liver went back to normal. Fatty liver disease is also something that happens as a result of chronic alcoholism. Okay? It's actually a reversible stage of alcoholic injury to the liver. With alcoholism, fatty liver disease is not produced because of consuming too much fat in your diet. That's not how it's produced. When you consume alcohol, the actual alcohol, ethanol, that you're consuming is metabolized by the liver. And one of the byproducts of ethanol metabolism is a substance called acetaldehyde. Okay. Acetaldehyde is hepatotoxic. Okay, so the liver does its job, it breaks down this substance, and one of the byproducts of the metabolism of ethanol is hepatotoxic. It is toxic to liver cells. And one of the ways that it's toxic to liver cells is that it interferes with the liver's ability to metabolize fats. So you get this self-induced impairment of lipid metabolism by the liver, and therefore this accumulation of fat within the liver. Okay. So this is a manifestation of chronic cell injury. Okay. And if the alcohol intake is stopped and the damage is reversed, this liver will go back to normal. But this chronic cell injury is also causing a chronic inflammation. And so the next stage after this is the development of cirrhosis, which is actually not reversible. Okay. But this is that first stage to that, the development of that. Okay. Sometimes you get water accumulation intracellularly. Okay. And the water that gets accumulated, the most common example of that happens when the cell's been injured and now you get this acute cell swelling. All right, and we talked about cell swelling in the context of hypoxic injury. Now, you can have hydropic swelling, the accumulation of water inside of the cell, whenever the rate of ATP production in a cell goes down, or whenever membrane integrity is impaired. Okay, so this accumulation of water inside of the cell can happen anytime you've got a reduction in ATP production, okay, for all of the reasons we talked about with hypoxic injury. But also whenever membrane integrity is compromised for some reason. Okay? And that can happen when you've got exposure to bacterial toxins, when you've got a viral infection, certain chemical exposure to certain chemicals can cause a reduction in either ATP production or membrane integrity. Okay. And as we talked about before, water accumulation inside the cell, there are certain points of no return where it no longer becomes a reversible cell injury. It then becomes, the next step is necrosis. And so in this slide on the top, we've got a portion of liver tissue from a biopsy where you see that there's this core of cells within the center of this tissue where there's a lot of white space. And that white space is because of bloated cells. And the cells that are the most bloated are dead. Okay? The cells that are the most bloated are dead. No cell gets to be that size without being dead. Okay? And then if you were to look at some of these cells in a much more high resolution way, you'll see intracellular structures. So here's normal cells. You see some endoplasmic reticuli, these sort of stacks of membrane here, okay? And then some mitochondria dispersed within it. And then on the right, you see swelling of the mitochondria, okay? And swelling of the endoplasmic reticuli, right? The filling of those membrane stacks with fluid. And once you start to see that, okay, so you have these nice, happy, normal-shaped mitochondria here on the left, and then on the right you get these big bloated dead mitochondria. Okay. And once you really start to see this kind of damage, this is permanent damage that the cell's not going to bounce back from. Right? These are mitochondria that no longer can have the electron transport chain or oxidative phosphorylation occur within their structure. Okay? Permanent damage. And so permanent cell injury is necrosis. Okay? Permanent cell injury that is traumatic in nature, okay, unintended cell death, is necrosis. And the reason why I'm saying that is because we actually do have a form of cell death that is intentional. Okay? And that form of cell death is called apoptosis. Okay? That's programmed cell death. And that's something we'll talk about at the end. But irreversible cell injury leading to sort of unintended cell death is necrosis. And the generic term for necrosis of cells is coagulative necrosis. And the reason why it's called coagulative necrosis is because as soon as this cell starts to die, as soon as the cell, the lysosomes start to burst open, the pH changes, it becomes more acidic, you start to see proteins denaturing and coagulating. Okay? So the intracellular material really starts to look very, very bad. Okay? Now, so coagulative necrosis is the generic term for death of cells and tissue. And then there are some other terms to describe tissue necrosis. Okay? Some other terms to describe tissue necrosis that is particular to the tissue you're talking about. And we've got, for example, liquefactive necrosis, caseous necrosis, and fat necrosis. And we'll talk about some particulars of each. But first, coagulative necrosis and the general characteristics of generic cell death. Okay? First and foremost, necrotic cells, they look like cells that are in a slow phase of exploding. Okay? They are bloated cells. Their shape is no longer regular. Okay? You can end up getting this bloating of the cell. You can get these blebs of membrane. Okay? And one of the reasons why the cell's shape is becoming really irregular is because that cytoskeleton, that nice cytoskeleton, those proteins are denaturing and they're coagulating and they're falling apart. Okay? You have bloated cells, you've got bloated organelles. Okay? The mitochondria are all bloated. The endoplasmic reticuli and the Golgi complex is all bloated. Okay? And then the nucleus undergoes a series of changes that are really stereotypical of necrosis. The nucleus of a cell that is necrotic, the first thing that appears is actually a shrinking of the nucleus. Okay? So unlike these other organelles that become bloated and large, the nucleus actually, as its proteins denature, it actually kind of shrinks. Okay? And sometimes that shrinking is called pynknosis. And then after the shrinking phase, the nucleus actually looks like it's just sort of exploded and fallen apart. Okay? And then lastly, cells that are dead sometimes look like they have no nucleus because the nucleus has just been broken down to such an extensive degree. Okay? And you can see here there's some necrotic tissue here with nuclei that are in various stages of dying, right? Some that are shrinking, some that are sort of exploding, and some that look like they're just missing from the cell. Okay. This is coagulative necrosis, the appearance of early coagulative necrosis in myocardial tissue of someone who's just had a myocardial infarction, a heart attack. So by definition, with myocardial infarction, there's been some death of myocardial tissue. And in this individual, the zone of infarction, the zone of dead tissue, is fairly easy to see because, first of all, it's darker in stain. And also, if you notice, if you look at neighboring tissue that's still healthy, there's a lot more white space around the healthy cells. Right? Well, excuse me, compared to the dead cells. Right? The dead cells have very little white space between them because all of the cells are sort of bloated and enlarged. Okay. Eventually, cells that are dying, their plasma membrane is going to degrade. Okay? And the intracellular contents are going to slowly sort of leak into the extracellular space. And eventually those cells are going to disintegrate and no longer be there. Okay? So necrotic tissue eventually kind of disintegrates, all the intracellular contents are spilled into the extracellular space, okay? And that tissue dies. When necrosis happens in organs that have very little to no connective tissue, okay, when necrosis happens in organs that have very little to no connective tissue, and the cells cannot regenerate, they can't divide and replace the necrotic tissue, what you end up with is something called liquefactive necrosis, where the tissue just sort of liquefies, and in its place is simply empty space, but really empty space that gets replaced by fluid. Okay. And so liquefactive necrosis is very characteristic of necrosis in the central nervous system. And you can see in this slide we've got an area of brain tissue that has necrosed. And if this brain tissue were still living and you could image it, it would look like what's replaced it is just sort of a cyst of fluid, a membrane encapsulated cyst of fluid. But since you don't have preservation of that tissue, what it looks like is just empty space. Okay. So liquefactive necrosis, cell death that happens in tissue of organs with very little to no connective tissue. Okay, there's really nothing there to maintain the integrity of the tissue, and those cells can't replicate and replace themselves. Fat necrosis is a form of necrosis that happens obviously in either fat tissue, right, in adipose tissue, or in organs that have large deposits of adipose tissue. Okay? And so large deposits of adipose tissue, you have deposits of adipose tissue in the pancreas, in mammary tissue. Okay? So organs where you have large deposits of adipose tissue, or simply in adipose tissue when you have necrosis, you get this form of necrosis called fat necrosis. And there's a really bizarre and interesting thing that happens with fat necrosis. If you remember, I said eventually when these cells die, the cell disintegrates and all the intracellular material is expelled in the extracellular space. Okay? And when fat cells die, you have fatty acids entering extracellular space, and these fatty acids react with extracellular calcium. Okay? They react with extracellular calcium, and when fatty acids react with calcium salts, you actually get the formation of soap. Yeah, it's pretty gross. But you literally get the formation of soap deposits in the extracellular space with fat necrosis. And in this slide, that slight haze that you see that's surrounding these adipose cells are actually, the haze is actually these soap deposits in the extracellular space. So a very unique form of necrosis. So caseous necrosis happens. Caseous necrosis is kind of an incomplete liquefactive necrosis. Okay. It happens in tissue where you have necrosis of tissue in organs where you have a minimal amount of connective tissue. You have some connective tissue. Okay. And the term caseous necrosis, the word caseous refers to, let me know what the root word the root of caseous refers to. Casein. It refers to cheese. And caseous necrosis was called caseous necrosis because somebody looked at that and said, that looks like cottage cheese. And it got its name from that. And that's literally the appearance of caseous necrosis. It's this sort of clumpy dead tissue where you have this incomplete liquefaction of the tissue. Okay? There's enough connective tissue kind of holding it together that it has this clumpy but disintegrated appearance to it. And a really common example of where you see caseous necrosis is in the lymph nodes of the lungs that are attacked by tuberculosis. Okay, and that's actually what this is here, where this is a lymph node within lung tissue that's been attacked by tuberculosis and has left this lymph node with a large zone of necrosis. And this is a picture of that lymph node within that lung tissue. You had your hand up? Okay. Okay. So again, it's a incomplete liquefaction of the tissue where there's enough connective tissue to kind of hold all of it together. And then finally, it's important to mention, if we're going to talk about cell death, it's important to talk about apoptosis. And apoptosis is different from necrosis. They're both forms of cell death, but apoptosis is what we call a programmed cell death. Okay. And within the genome of all of our cells, okay, within the genome of all of our cells is a suicide pathway. Okay. There are instructions in every cell in our body that, when turned on, cause that cell to literally commit suicide, to initiate this apoptotic program that's going to lead to its own death. Okay? And cells in our body are much more altruistic than we are. They are willing to take one for the team at any time when instructed. All right? And this is how they do it. This is how cells are often instructed to kill themselves, and they dutifully comply. Okay? And so what happens when this program is initiated, initiation of this program means that the cell is instructed to transcribe and produce a set of proteins called endogenous endonucleases. Okay? Endogenous endonucleases. I don't know if it's written anywhere there. But so endogenous obviously means coming from the inside. And endonucleases are proteins that go in and start cleaving portions of the chromatins. Okay? They start cleaving chromatin. They start breaking up segments of the genome. They start breaking up segments of DNA. Okay? And once they start breaking up these segments of DNA, it triggers this progression of apoptosis where the cell starts to die. And in this progression, the cell first appears like it is shrinking. Okay? So you got the cell starts out at normal. Something triggers the pathway. You start to produce these endonucleases. The nucleases start to break up the chromatin and the DNA, and the cell starts to shrink. Okay? And it looks as though all the organelles and the cytoplasmic material start to clump together. Okay? And the nucleus starts to look like the nucleus of a cell that's dying. It starts to collapse in on itself, and then it starts to sort of dissolve. Okay? The membrane starts to look like you get this blebbing, like we saw with a necrotic cell. And then eventually, the cell sort of breaks apart into these vesicles that we call apoptotic bodies. Okay? And then the apoptotic bodies are phagocytized by macrophages and other phagocytic cells, immune cells in our body that sort of clean up the mess. And so while the necrotic cell looked like a cell that was bloating and exploding, an apoptotic cell looks like a cell that's sort of imploding. Okay? So an apoptotic cell looks like it's sort of collapsing into itself, as opposed to a necrotic cell that looks like it's exploding outwards. Okay? So cells are triggered to apoptose in lots of normal, in the context of lots of normal functions. Okay? Whenever a cell's existence is no longer needed, the body might initiate apoptosis in that cell. However, sometimes you get the initiation of apoptosis that's inappropriate. Okay? So sometimes apoptosis is triggered inappropriately. And that can happen when the cell senses any degree, or a significant degree, rather, of DNA damage. Okay? So when a cell senses that there's a critical number of mistakes in its DNA, it immediately initiates apoptosis. Because what's the danger? If you get too many mistakes in your DNA, what's the danger? What's that?
Replication.
It could replicate and make copies of that mistake. And what could some of those mistakes include? What could you end up producing? What kind of cell? A cancerous cell. Okay? Some of those mistakes or mutations might favor cancerous growth. So as soon as the cell notices that its DNA starts to become unstable, it initiates apoptosis and it takes itself out. Okay? But let's say a virus infects the cell and it injects its own DNA into the cell's DNA so that it can replicate itself. Okay? Sometimes cells recognize that abnormal strand of DNA and initiates apoptosis as a result. Okay, so viral infection can trigger apoptosis. Certain kinds of membrane and mitochondrial damage, okay, can trigger apoptosis in a cell. certain types of stress, especially stress inflicted to the endoplasmic reticulum, okay, can trigger apoptosis because it's going to affect the cell's ability to synthesize protein. Okay. And then cells can be instructed to apoptose by the immune system. Okay. And that can be protective, okay, because part of our immune system is actually designed to recognize abnormal cells like cancer cells, right? And so, or abnormal cells that are infected by a virus. Okay? So getting instructions to kill yourself by the immune system can often be, and is usually, a good thing as far as maintaining stability of the organism. But what if you have an autoimmune disorder, right? Where now your immune system is not really working in your favor. So now you have your immune system instructing otherwise perfectly fine and healthy cells to die. Okay. So apoptosis is programmed cell death, but it can be stimulated by a pathological process.